What is silicon carbide? Silicon carbide is a compound semiconductor that consists of covalently bonded silicon and carbon atoms in a tetrahedral arrangement. Silicon carbide exhibits polytypism. Different crystal structures are possible depending on the stacking sequence of identical layers. For silicon carbide, there are three possible ways a layer can be stacked on top of the layer below it, commonly referred to as A, B, and C. Silicon carbide has over 200 stable polytypes. The three most common polytypes of silicon carbide are 3C silicon carbide, 4H silicon carbide, and 6H silicon carbide. 3C silicon carbide is the only known cubic polytype, has a stacking sequence of ABC, and is also known as beta silicon carbide. Non-cubic polytypes are referred to as alpha silicon carbide. 4H silicon carbide and 6H silicon carbide both have hexagonal crystal structures and have stacking sequences of ABCB and ABCACB respectively. How does the polytypism of silicon carbide affect its physical properties? Across all polytypes, mechanical properties are nearly identical. All polytypes, regardless of crystal structure, feature a network of covalently bonded silicon and carbon atoms. These bonds have an extremely high bond energy of 4.6 electron volts, giving rise to silicon carbide's unique thermal and mechanical properties. To list a few, silicon carbide does not melt and instead sublimates at 2830 degrees Celsius, is very chemically stable, and is one of the hardest materials on the planet. At room temperature, 6H silicon carbide has a Young's modulus of between 380 and 700 gigapascals, depending on the direction of uniaxial loading. Because there is so little polytype dependence on the mechanical properties of silicon carbide, polytype control is generally irrelevant for mechanical applications of silicon carbide. However, the electrical properties of silicon carbide greatly vary between polytypes. This is a result of polytypes having very differing electronic band structures. For electrical applications, polytype control is crucial. Pure crystals of a specific polytype must be grown so that the silicon carbide has the desired electrical properties.
And here's SSC, one kind of the three silicon carbide. SSC stands for sintered silicon carbide. It is manufactured by adding sintering aids, which have to form liquid phase at sintering temperature. And this allows the grains of silicon carbide to bond together, as shown in the picture. This picture shows one example of SSC. And here's the table of SSC properties: density, bulk modulus, cluster modulus, shear modulus, and hardness. And as you can see, it has a high hardness, it has a low density compared to other steels, approximately similar to aluminum, and it has a good wear resistance, and it has an excellent corrosion resistance. So this is pretty good in composite armor protection systems. As you can see, this picture shows one example of the armor system, because of its high hardness, compressive strength, and elastic modulus. And now let's move on to the next part of silicon carbide. MBSC, nitrogen-based silicon carbide. It is produced by firing mixture of high purity silicon carbide and silicon in nitrogen gas at usually high temperature, about 1400 Celsius degree. So those silicon carbide is bonded by a silicon nitride basis during this nitriding. And as you can see, the ratio between nitrogen and silicon carbide, standardly usually for 70% of silicon carbide and 30% of silicon nitride, will determine their properties. Here is a table of NBSC properties: density, Young's modulus, and band strength. As you can see, it has a high mechanical strength, which can be sustained up to 1600 Celsius degree, and it has a great chemical resistance against molten salt, acid, and halogens. MPCC also resists weathering through the non-ferrous metals, and it, just like SSC, it has a great wear resistance. And BSC also acts as a semiconductor, can act as a semiconductor at high temperature. So here is a typical application of an MBSC. Yes, that is brick. MBSC is used in brick for process cooling and furnaces. That's because of its superior material mechanical strength and endurance. And now let's move on to the last but not the least, silicon carbide, RBSC, reaction-based silicon carbide. It is produced by insulating complex made of mixtures of silicon carbide and carbon with liquid silicon. The ratio of silicon carbide to carbon and their particle distribution matters a lot because they determine the properties. And here's the table of RBSC properties: density, Young's modulus, band strength, and hardness. It has a great resistance corrosion as well as abrasion, and it has high strength at high temperature, and it displays a good dimensional control of complex shapes. And because of its high temperature strength, oxidation resistance, and thermal shock resistance, it is used in kiln furnitures. It enables those manufacturers to produce low-mass kiln supporters.
One of the advantages of silicon carbide as a semiconductor is its relatively high band gap. The critical electric field strength refers to the strength of an applied electric field that results in electrical breakdown, where electric current flows freely through a semiconductor. This property is important for many power applications and increases with band gap and doping density. Alpha silicon carbide has an 8 times larger critical electric field strength than silicon, the most used semiconductor. Another benefit of silicon carbide as a semiconductor is its relatively large thermal conductivity of 4.5 watts per centimeter Kelvin at room temperature. Its ability to conduct heat allows it to dissipate power more efficiently and makes silicon carbide a strong candidate for high temperature applications. In the present day, two of the most common uses for silicon carbide semiconducting properties are Schottky diodes and MOSFETs. The biggest advantage of using silicon carbide in power switching devices is the minimization of reverse leakage as a result of silicon carbide's high bandgap energy, compared to silicon Schottky diodes, which have high reverse leakage currents and are accordingly restricted to low voltage applications. The low reverse leakage of silicon carbide Schottky diodes enables it to be used in high voltage applications.
I would like to continue the discussion of the applications of silicon carbide in other various industries and facets. But what I want to bring to light to you is the use of silicon carbide as a means to synthesize diamonds. The conventional way of making synthetic diamonds usually have high costs for relatively low yields. The high expenditures usually coming from creating a high pressure environment and plasma activation. However, the silicon carbide provides a more lucrative alternative to subvert that. The environments used to create synthetic diamond using silicon carbide does not exceed temperatures over 1,000 degrees Celsius and is performed at ambient pressures. As with the nature of silicon carbide, of it being capable of being both a hexagonal and cubic structure, this method is able to create both hexagonal and cubic structured diamonds. And not to mention, though the diamonds created using this method has very similar properties to those found in the natural world, with an identical or a tested identical Vickers hardness of 50 gigapascals and a near similar Young's modulus value. The mechanism to synthesize diamonds using this method is shown on screen right now. The silicon carbide is presented in a chlorine-containing gas environment, where the gas extracts the silicon from the silicon carbide. The chlorine gas itself is a mixture of both chlorine gas and hydrogen gas, with with a 2-to-1 ratio of chlorine gas to hydrogen gas. The higher ratio of that typically yields greater diamond synthesis yield. But the hydrogen gas is there to motivate the reaction forward and not have it fall back. Another application I would like to mention is the use of silicon carbide as an abrasive, or more specifically as a brake. Silicon carbide has various properties that would lend itself to be a great candidate to be one of which being its lightweight property, comparative to its metal alloy counterparts, to say something like an iron alloy brake. A silicon carbide a compository brake only requires a percentage of it to be made of silicon carbide, while the rest can be made of something equally lightweight, like carbon fiber reinforcement. But another aspect would be its resistance to corrosion. Since it's a ceramic, it's far more resistant to corrosion than its metal alloy counterparts. But I do believe its most defining feature of being a good candidate of a brick is its capability of withstanding high temperatures. As mentioned earlier in this presentation, it's it's used as a furnace insulation. Even at high temperatures, the silicon carbide compository brick is able to maintain a consistent friction factor.
One place where we will see silicon carbide in the near future is in jet engines. Here we have a diagram of a GE aviation jet engine. The highest temperatures and pressures occur in the sections closest to the combustor, the high pressure compressor and the high pressure turbine. As the plots show, pressure and temperature can exceed 40 atm and 1500 degrees Celsius in these sections. In the proposed aerospace planes of the future that will be able to fly between Earth's atmosphere and space, these sections will need to withstand more than 2000 degrees Celsius. As a result, they need to be made of extremely durable materials, and silicon carbide is the primary candidate. Typical high-pressure compressor and turbine materials are nickel, cobalt, chromium, aluminum, and yttrium superalloys. As this phase diagram shows, their melting temperatures can exceed 1600 degrees Celsius depending on composition. However, its ability to withstand temperatures up to 2500 degrees Celsius combined with other factors makes silicon carbide the better suited material for use in future jet engines. However, silicon carbide also has a few disadvantages compared to superalloys, the primary one being its brittleness. In order to quantify this brittleness, I'll briefly explain the concept of fracture toughness. Microscopic cracks exist at the surface and inside of material. When stress is applied, it gets amplified at the tips of these cracks. Metals, which include superalloys, fail through ductile fracture, in which plastic deformation occurs at the crack tip when the stress there exceeds yield strength. Therefore, there is extensive energy dissipation, and crack length only increases with an increase in stress. Ceramics, such as silicon carbide, on the other hand, undergo brittle fracture. They do not have an equivalent energy dissipating process due to their lower dislocation mobility. Therefore, there exists a critical stress, given by this equation here, at which the crack begins continuous propagation without any further increase in stress, resulting in failure. When a stress acts on a crack perpendicular to its length, the fracture toughness, or K1C, is equal to y times sigma times the square root of pi a. It has units of megapascal square root meters, and a lower K1C means that a material will fracture under a lower applied stress. The fracture toughness of silicon carbide is 2 to 4 megapascal square root meters, which is very low. To avoid fracture in jet engine parts, they're instead made from silicon carbide ceramics matrix composites, which I will refer to as SiC CMCs. I'll give a brief overview of what a ceramic matrix composite is. A composite material consists of chemically or physically distinct phase distributed within a continuous phase, which is called the matrix. In a SiC CMC, the distributed phase is silicon carbide fibers. Fibers of a given material have a large aspect ratio, or length to diameter ratio, which gives them more flexibility and higher strength than the bulk material of the same composition. The primary role of these fibers is to impede crack propagation in the matrix by introducing mechanisms that can absorb energy, similar to plastic deformation in metals. These mechanisms include debonding of the fiber matrix interface and bridging of cracks in the matrix. The most common silicon carbide CMC is composed of beta silicon carbide fibers with diameters between 8 and 15 micrometers embedded in a silicon carbide matrix, which can be any of its numerous crystal structures. We saw earlier that the fracture toughness of K1C of monolithic silicon carbide is 2 to 4 megapascal square root meters. The fracture toughness of SiC CMC is 41.5, which is roughly 10 times greater. This is why we will be seeing SiC CMCs in future jet engines, since they are relatively resistant to fracture in addition to being able to withstand high temperatures.